Hey everyone, thank you for joining the session. Welcome everyone, and yeah, I'm excited to present some AI stuff. That's all the hype, right? So yeah, before we get into the session, a couple of minutes about me. I'm Bharath Nallapeta. I work as a senior software engineer for Mirantis. I've been in and around Kubernetes for a few years now. I've worked with companies that are almost like startups to large enterprise companies as well. So my career path itself is sort of um, mirroring the platform engineering and the Kubernetes at scale kind of journey. And then when I moved on to another startup, a Swedish-based company, I was working on soft multi-tenancy. So it's perfect for companies or people who are looking for solutions that are probably, let's say, one, two, or three clusters, and then your small teams and your small number of people. That's ideal. So soft multi-tenancy is nothing but you have a single cluster and then you divide them into isolated tenants, right? So you achieve isolation using software where the hardware is still the same, right? So that's good. There's been quite some solutions in this space, but then it certainly has its limitations, right? That's where the real multi-tenancy comes into picture, and that's where a lot of companies, a lot of people are trying to find a good solution for, right? So Cordon, I'll come to Cordon in a bit, but before that, the problem statement is this: that multi-cluster, multi-cloud solution is really important, right? I know the title says AI. You all are waiting for, to see some AI apps run. I'll get to that soon, but I'm just taking a few minutes in the beginning to lay the foundation that be it AI apps or any other application that's running on scale, you need a solid platform, right? You need a scalable, extensible platform, and that's what Cordon provides, right? So let's get started. Right. So, like I said, platform engineering has been around for a while, and all of us have used one or more of these clouds at some point in our lives, right? And companies usually have a mixture of these things. So there's private data centers and then private cloud and then public clouds and edge networks and all that, right? So as Kubernetes has matured, we have found it more and more difficult to manage this entire cloud, right? So although it was supposed to be just one single, contract or whatever with a particular cloud, and then we're done, is not that. Like I said, the ecosystem we built around Kubernetes requires us to communicate with so many components at scale between all these, let it be services or components or companies and products, right? The need for platform engineering in order to run scalable AI apps or data science apps or any apps that requires a lot of compute is quite strong, right? So from a developer's perspective, we'll be looking for a self-service platform. And from a managerial perspective, from a DevOps perspective, we'll be looking for operational, simplicity combined with ease of customization, right? So let's say a particular team has asked for 16 gigs of RAM, and then four vCPUs, and then three nodes, and you get that. But a different team has different requirements. That's where the customization requirements becomes quite strong. So in order to support a wide variety of audience, you'll need to properly have the power to perform these customizations. Visibility and control is again really important. Um, the cost can get out of hand really quickly. So if you don't have a complete view and understanding of how many clusters you've provisioned, who's using what, who's using how much, and all these things, the control mechanisms, will become really important. And security and compliance, definitely right. So security and compliance should form the bedrock of any enterprise platform engineering team or any infrastructure that you're trying to build. This should always be there. This shouldn't be a peripheral thought, but rather this should become the core values on which you build your platform. Now, in order to accomplish this, and in order to get this done and reach this, platform engineers also have certain needs and what are they building for exactly, right? So, like I said, multi-tenancy, the example I gave you between soft multi-tenancy and hard multi-tenancy becomes all the more important here. Platform engineers and platform engineering teams are usually designed to handle things at scale, which means catering to hundreds of customers. Then there are these AI/ML and edge and IoT applications, which is quite important to um, it's quite important for the hardware to cater to run these things. So there's the generic hardware, and then there's maybe like slight tweaking of the hardware in order to optimize the running of these applications, right? And then of course, like we've already covered, this hybrid multi-cloud and high availability, all these things. So just to again reiterate, multi-cluster, multi-cloud is becoming the new norm. Whether you want to run your enterprise applications, scalable AI/ML applications, data science applications, or any domain, right? This sort of becomes a norm. I've just put up some stats here, as you can see. This survey reveals that 76% of the organizations have implemented multi-cloud strategies, but only 29% of them have actually adopted a proper platform engineering. Most of them want to run multi-cloud apps. Most of them want this multi-cloud, multi-cluster environment. But in order to properly get philosophical plan with proper architecture and adopting platform engineering, there's a there's a case of lacking in this area. That's why I think there are choices where we start with nothing, like at the start, right? When we want to build a platform engineering service, we understand that the cost of building this whole thing is expensive, right? And it is not scalable at all. Then the next immediate solution or the next immediate process or thought that we'll go into comes DIY open source. This is great, right? Especially Kubernetes has accepted and accelerated open source development so much that we really can't imagine a world without it, right? So it's really good, but there are just too many options for any single thing that you pick, where you have to pick and choose between components for any particular result, right? Then there's a proprietary solution. Of course, famous clouds like AWS, GCP, Azure, all these guys provide solutions, but then they provide solutions for their own cloud, right? So we've all seen cases recently. What happens when you have a vendor lock-in? It's never really good, especially when you're thinking of a huge infrastructure and a huge cloud. So this becomes vendor lock-in, and of course, you're completely dependent on them, right? So the feature set and the extensibility completely becomes dependent on that particular cloud, right? So then there's the fourth solution, which is enterprise grade open source solution. So what we're talking about here is using the existing open source tools and then combining them in a way which presents the best of both worlds. So you've got the open source solutions combined with the enterprise grade solutions as well. Let me jump into k0rdent now. This is what k0rdent does. At a very brief scale, k0rdent empowers you to do multi-cluster, multi-cloud provisioning and management of Kubernetes clusters at scale. In order to work with this, you don't need to understand or learn any of the IAC code, infrastructure as code solutions. You don't have to use things like Terraform or Crossplane. That's a whole different world, right? You would just need to work with YAML directly and Helm charts. That's the configurable and ease of use that k0rdent provides. So we'll talk about two things: cluster templates and service templates. I'll jump more into it when we jump into the demo section. But essentially, what you have is cluster templates and service templates. That's basically operating your entire, k0rdent. The architecture of k0rdent goes like this, where you have KCM, that's the cluster manager. Then you have KSM, that's the state manager or the service manager. Then you have KOF, which is the observability and FinOps wing, right? So the k0rdent cluster manager is responsible to actually provision the clusters, which is the day zero operation. It interacts with all the upstream cloud components, whether it be AWS or Azure or GCP, right? vSphere, OpenStack. And then service manager is responsible for the day two operations, wherein you'll actually want to deploy applications. We'll see more of this in this particular session as well, because in order to run AI apps, you got to prepare your cluster to be AI ready, right? And that's where service manager comes in handy, right? Just a quick note before we move on. So essentially, what we're talking about here is a complete internal developer platform, right? So IDPs have been there for quite some time. It's been congregated into specific domains. And when we talk about Kubernetes and IDPs, what we want is a repeatable platform engineering mechanism where you as a platform engineer are able to provide your team with a platform that's catered for their use case. At the top layer, when as you can see, there's like MLOps, AI Ops, HPC, Edge IoT, and so on, right? This could be anything. And today we're going to focus on machine learning and AI. This entire stack remains the same, and the infrastructure provider remains the same, and your application layer, the workloads, could be anything. That's the flexibility that k0rdent provides in order to create an IDP. So before I talk about this, right, briefly, I want to mention why AI is suiting so well with Kubernetes. You can run AI. I mean, it's moving so fast that we can literally run AI on Android devices now. We can run them on our laptops. We can even run them on CPUs. We don't even need to depend on GPUs, right? So there's all sorts of hardware that's getting enabled day by day, but for AI-based applications. But if you're talking about enterprise AI applications and you want to scale stuff and you want to maintain that availability, then Kubernetes presents itself as a very good solution, as a very good platform, right? So let's say you have an AI app that's using PyTorch, and then you run it on your Linux machine, which has a GPU node, right? This would be okay, good enough for development purpose. But when you think about serving it up for users, optimizing the usage, there are some limitations, right? So Kubernetes presents itself here as a platform that can do these things well. Kubernetes can help auto scale models. It can scale down to zero. It can scale up as and when the requests are coming in. You can easily control the number of replicas, right? You can divide this among multiple servers across clouds. You can distribute the workloads, right? All these things would become extremely difficult, if not impossible, to do it on traditional server-based methods. Of course, I use the word impossible very, carefully here. Of course, anything's possible, but then there'd be a lot of, manual intervention in a lot of shortcuts that we'll need to take to make that possible. Whereas Kubernetes will provide this as, as rather a feature in the nature of the platform itself. Then comes the choice or selection of the compute, and then how do you make that compatible for Kubernetes? So to get back a step and then understand, in order to run AI applications, you'll of course need a GPU node, right? That GPU would need to be enabled by installing certain drivers from NVIDIA. So again, here we'll focus exclusively on that. Is like the whole demo is based around that, wherein we're using NVIDIA Tesla G4 based GPUs. And then you'll need to make sure that the container runtime is also installed in order for Kubernetes control plane, Kubernetes nodes to understand that that particular node has GPU nodes, and we can schedule, workloads there, right? I know this might sound confusing a little bit, but soon when we jump into the demo, I'll make these things a little more clearer, right? So if any of you guys have tried doing all this manually, it's a lot of effort. There are just one too many things that one has to do. In fact, there's a running joke that NVIDIA drivers have been the same for like 5+ years, and nobody's just gotten it to work smoothly in the first go, right? There's always some issue or the other that keeps cropping up. What Cordon does with the power of service templates, which I mentioned, is it'll help all these make it possible, and it'll help the developers to deploy these things quite easily, right? And for this demo, we have chosen KServe Knative in order to do the scaling up and down, right? So this is the second layer of things. So the first thing I talked about is preparing the hardware and making it possible for in order to run GPU enabled workloads. And then the second layer becomes installing KServe Knative and letting that handle all the auto scaling bits, right? So once again, what I want to emphasize is that the NVIDIA GPU Operator, Kscale, Knative, Prometheus, Grafana, all of these tools are open source, and all of these have, most of these have Helm charts, and this is continuously being developed by different communities at different scales, right? So all we're doing is trying to bring all these things together into a single platform and make the experience as smooth as possible. So a little bit of introduction or trying to set the context here. This is my kind cluster, and this is where I've installed Cordon. And these are the typical components that are installed, post installing Cordon. You have a bunch of controllers here. So this is the upstream CAPI controller, and then Kappa for AWS, OpenStack, vSphere, Azure, right? Earlier, I mentioned that Cordon uses upstream open source projects, and that's CAPI, right? So it utilizes the controllers and the entire CAPI ecosystem in order to actually provision and deploy the clusters on whatever cloud we wanted to deploy to. Then there's a bunch of Cosmotron controllers. So Cosmotron controllers is the control plane manager sort of for Cordon. So Cosmotron itself is an independent project which handles the provisioning of Kubernetes clusters, right? And then there's a bunch of KCM nodes itself, KCM pods itself, right? So these are the components. Now, if we see, let's first look at cluster templates, right? So I mentioned two things. One is cluster templates and one is service templates. So the cluster templates are templates which basically contain a reference to the Helm charts. And the Helm chart contains references to all the templates that has to be applied in order to provision a Kubernetes cluster, right? So right now we have support for all these clouds. GCP was released quite recently too. And what it essentially does is reference this template in your cluster deployment, and then it provisions all the resources such as your cluster, your Azure clusters, if I have to take an example for Azure, then your machines, Azure machines, and so on. These are all upstream CAPI objects. That's cluster templates. This is what you need in order to tell Cordon where you want to install and how you want to install the particular cluster. Then you have service templates. These are the day two operations, like I mentioned. So we have a bunch of service templates, and we have a website called catalog.cordon.com where we have packaged all these service templates into our catalog. And this is an ever-growing catalog, and obviously we welcome open source contributions to this. Right now, I think about 20 plus or 30 plus services are already there. And you can see, right, some of the famous ones are, I've installed it here while I was, testing for the AI thing. So like Cert Manager, Secrets, Gateway, GPU Operator, Ingress, and all that. And if you notice, there's Ingress 411 and then Ingress Nginx 411.3, 411.0 and 411.3, right? So I installed both the versions here to showcase the versioning capability here as well. So, like I mentioned, this is the kind cluster. This becomes your management cluster, right? So while I'm using kind, this could be any Kubernetes cluster on any cloud itself. So that becomes your base. And you'll use this cluster to provision multiple other clusters. And if you deploy all the service template with different versioning as well, what happens tomorrow is that if you want to use reference a particular version of Nginx in one cluster and a different version of Nginx in another cluster, you get that flexibility, right? That's why I have multiple versions of Cert Manager and Ingress based on my requirement. And finally, let's see the cluster deployments. So these are the available cluster deployments right now. Yeah. Before I explain that, let's first go ahead and apply a cluster deployment right now for this demo. All right. And right. So that's started, right? So we should be able to see a cluster in less than 10 minutes. It might be very surprising to some of you because unless you're really tied down to a vendor, if you do this, self-service Kubernetes cluster provisioning yourself, you would have definitely experienced the pain of, provisioning a cluster end to end with everything just working. And this is just not provisioning a cluster, but also installing the other AI services as well. So let me open or let me show you. This is a long running cluster that I have. Until that is provisioned, I'm going to show you this, or rather, give me a second. All right. So let's look at the YAML directly, the YAML which I applied. So every cluster deployment has like 3 or 4 main things. The one, obviously, the important thing is the template, which I mentioned, the cluster template. You gotta tell k0rdent which template you want to use. There are different versions, and then there's standalone and hosted. Standalone is when you want the control plane and the worker nodes to reside in the same cluster. Hosted is when you want your control plane to be, in one central place, and then multiple child clusters where the child cluster will just have the worker node. So it's a central management kind of thing. Then you have a credential reference, which is nothing but a secret that's wrapped up into this credential object, right? So these are nothing but the same credentials that you'll use to interact with your Azure cloud. And then down here, we have the services, right? Down here, we have the services. And in this particular one, I've just installed the GPU operator, right? So we'll go deep into this with our actual cluster that we just provisioned. And the last bit will become the config, right? So config is cloud dependent. So for Azure, you have all these variables, all these fields. And similarly for OpenStack, for AWS, and so on, there'll be different fields that is appropriate for that particular cloud. These are again following the upstream CAPI and Kappa cloud controllers, and all the fields are referenced to whatever it's set there, right? Now let's see what is the status of a thing. I think it's still coming up. Then in the meantime, let's take a look at, yep. So here in our services, right? In our services for this particular demo, talking about AI scaling, this is what is important. The entire manual process of installing all the dependencies and finally Knative and KServe is all taken away and then abstracted into a list of services like this. So earlier, before this, I installed the service templates from the catalog. And once the service templates are installed, which I listed with kget service templates, all you need to do is reference all of the service templates in this. So let's take a look at them. So the first one is the GPU operator by NVIDIA, which is something I already mentioned. This is required in order to make the cluster GPU ready and explain to Kubernetes that there are GPU nodes attached to this hardware instance, and we can actually run AI workloads, right? That's what this does. Then there's Istio. Then there's Cert Manager, right? And then finally, we have the Knative and KServe components, right? So all these are service templates that are referenced, and the service template is referring a Helm chart. Yeah, let's take another look. All right, I think while that is still getting provisioned, let me go ahead and jump into the second part of the demo. So in order to showcase, in order to deploy stuff, right? I've created a bunch of inference services. And then I have a central pipeline called Neural Babel, which is nothing but a deployment supported with a config map and a service and a virtual service, right? Virtual service is a CI, which is of Istio. I'm sorry, it is of Knative, right? And then there's these three inference services, right? To give a quick overview of what we're trying to accomplish, the demo will showcase an end-to-end display of translation, voice translation, basically. So I speak in English and then I get an output in the desired language. This is done completely using AI, and this is running on the Kubernetes cluster. And I've split this into three distinct services. So the Cube Whisperer basically takes an audio and then gives text. So that's basically, the audio to text service. Then the translation inference service supports translation between languages. So it translates the text from one language to another. Then there's the TTS service, which does the final conversion from text to sound. So the Cube Whisperer uses OpenAI's Whisper model, and the translation service uses Meta's NLBB model, and the TTS service uses CoQ's TTS model. All these are open source. All these are available for everybody to use. But what I've done is I've taken the upstream models that are available and then built an app around it, and then built three similar apps like that for each purpose. And finally, Neural Babel is the one that's converging them all, right? So let's take a look at each inference service to get a better idea. So as you can see, this is an inference service from KServe. And we have the container, the env variables, the image, and it's pretty standard Kubernetes spec, volume and everything. So just a brief about this, there's an image that I built, of course, from the repository that I have. And then this is the customization that the image provides. So you can select all these and set to whatever is needed for you. I've currently used a Whisper Tiny model. There's base, there's large, and there's so many other models as well, right? And similarly, there are many other environment variables that you can set based on your requirement. And now the important thing. So we see these annotations, right? So this is how we actually accomplish the scaling part. So KServe is smart enough to understand when it's getting too many requests and it needs to serve those requests. and it'll scale it up. So what I've done for demonstration purpose is I've set these two where minimum scale is 1 and max scale is 2. Typically in enterprises, it's a good practice to actually set this to 0 because you don't want your GPUs to be running and consuming and costing you money when there's actually no real request coming your way, right? So this is typically set to 0. That means the GPU is sleeping. And then you set whatever number you want for max scale. What happens is when the first request hits, KServe intercepts that and then immediately scales to 1 to start with, and then addresses that request. Let's take a look at the other ones as well. This is not really that different. Again, it's a different image that does a different thing with exactly the same configuration for scaling, and then a bunch of environment variables as well. And then the last one, which is the TTS service, has pretty much the same thing, right? A bunch of environment variables, you can provide what model you want, and then your image, and then the same auto scaling analytics. And then we have the neural label, which is a pipeline that combines all these things. I've built an image around it, and then it retrieves all these endpoints using a config map. This is standard pretty deployment file. In the config map, I provide the endpoints. So for now, since this is a local environment, I've used nip.io so that it routes it back to my machine. And I've set the source language as English and then target language is French. And then provided these 3 endpoints. Right? And where to get those endpoints? See external IP. So you might notice that it's different. That was like 52 something and this 74 because I was working off with another machine right here. And that's probably why I edited that. Yep. So this is the machine that has 52.172.29.109. And the file also contained that, right? And before running the actual test, let's go back and see. Awesome. So a demo cluster is ready. Kubeconfig for this demo cluster is actually stored as a secret in the same namespace, right? So it's suffixed with -kubeconfig with the name of the cluster. I'm gonna do this and export it to basically that path. Open a new tab, and then we named it demo, right? Demo assure. Yeah. Then when I do this, here we go. So this is the cluster that we just provisioned. Has 1 control plane and 3 worker nodes as mentioned in the configuration in the cluster deployment. And then let's see the namespaces. Let's see cert manager, right? Istio, and so on. So finally, let's verify KServe, right? Perfect. And also verify Knative. All right, awesome. So you see what just happened, right? So this is the cluster, and to review the cluster deployment file again, because we've submitted all these service templates in the service spec region of the cluster deployment, it has automatically provisioned all these services for us, right? Another check we can make is, I think this would take a little bit more time. Yeah, as you can see, there are so many pods that needs to be actually deployed, and then NVIDIA does a bunch of stuff. So we got to give it a little more time, and then all the pods will be completed, and then we'll have a node ready. I'm going to switch back to the server that was already there, and just to show you the yeah, this is what you see. So allocated resources, yeah, this is what I was trying to find. So this server right here has already, been provisioned or been configured with the same set of configuration that we just saw. And in the interest of time, I just provisioned this cluster before the demo. And once the NVIDIA GPU operator is done, this is what you'd expect to see. That it recognizes the it recognizes the GPU and then it puts these labels, nvidia.com/GPU is one, along with the rest of the stuff, right? CPU and all that. And you can even observe this in the label section of the node as well. It has a bunch of stuff. So finally, let's test this out. So I've got a script here in order to test this out. Let's do test deployed. I have this cluster, everything set up. I'm running the test script. I'm not sure if it'll actually play back the audio. The script actually does this entire conversion and then plays it loudly, but I'm wearing earphones and I'm not sure if you can actually hear the sound or not. Let's see. So I've got an audio file. It'll take that audio file. It is converting that to text and then English text to French and then French text to audio back. All right. I think I really can't play it back right now because I'm wearing earphones and I could hear it. So while it's playing translated audio, it actually played it back, right? So this is the end-to-end pipeline. Now, let me open the same thing in another tab. While we created these three inference services, what KServe does is it deploys these pods, right? So these pods are maintained and controlled by KServe, and we just have to work with the inference services, right? And these pods are all spawned by that. Okay, so yeah, it's sort of the same thing that I wanted to show, but basically it scaled it up to 2 pods and then it's terminating now. Let me run another script where we send concurrent requests. And let's do watch. There you go. So if you remember, we had set the initial minimum scale to 1 and then max scale to 2. Over here in the script, what I'm doing, I'm just sending requests one after the other with a 2-second waiting period. Because if you just send like 100 requests at a time, then I've seen that the app crashes, or crashes is not the correct word. It takes in the request, but then immediately fails it. So I'm just giving a 2-second cap. And then as you can see here, the first pod in the pipeline, which is KubeWhisperer, comes up. It had 1. Now the second one comes up, pending containerizing and eventually running. And then the second one is also come up. So the reason why Lexi Shift is not coming up is because the underlying model itself is capable to handle this workload. So this is using Meta's NLLB model, and text to text is somewhat, as you can understand, quite low power consumption compared to audio files and video files, right? So with the kind of requests that we are sending, 30 requests, Lexi Shift has been able to handle all those requests with just 1 pod, whereas the text to audio conversion and then audio conversion back to text, which is the Voxtraga and then KubeWhisperer, was not able to handle it within just 1 pod, so it spawned up more pods. That's where you see the smartness of KServe and Knative as well, that it's just not blindly increasing or scaling up the pods, costing us money. It's actually looking at the workloads that it's getting and then dynamically scaling up only when it's required, right? So when I do this, in this moment, you can observe like there's 2 Vox and then 2 Cube and then 1 Lexi and then 1. So this is not an inference service. This is just a pipeline. So ignore this. And you can already see that since we've stopped, within a few seconds, it went back from running to terminating. And in a few seconds, you can observe, yeah, even Voxtraga is gone and everything's again back to normal with, minimum scale of 1 replica for each. So I really had to push the number of requests in order to get Lexi Shift itself scale up to 2. And I was able to do that far better when I was actually directly sending queries to LexiShift model instead of the neural label model. But anyway, it's the point of us to showcase the other world as well, which is really nice, right? And a final confirmation. We have everything back to minimum scale of one. So I know there was a lot. I'll take just maybe a couple of minutes to summarize it all. So the base, platform engineering, the need for scalable, repeatable, customizable platforms, how it's very complex, and then how Cordant helps there. Number one. Number two, why Kubernetes is perfect for AI, for all the challenges that it provides. First of all, in order to set up the hardware that's required to run, that's one. And then once you've set up all the hardware, the challenges it presents in order to scale it up and in order to basically cater to larger audience, not just larger audience, even the other way is true, right? So even the other way of scaling down is also true, which is extremely difficult to do it without Kubernetes. And that's why Kubernetes is a perfect fit. And Kubernetes with Cordant here, which provides the backend underlying platform engineering and accelerates AI ops or MLOps, whichever way you look at it, is what I try to present here, right? So the NVIDIA GPU operator, mention it as a service in the service spec, done. Now your GPU is ready. Now your hardware is ready. It's GPU enabled. Scaling down and scaling up KServe and Knative, install it as a service again. Prerequisite for that is Istio and Cert Manager, no problem. Just mention it in the service spec, it's ready. So before this, if any of you guys still want to try it now, I request you guys to try it out manually in order to install KServe, Knative, and all its dependencies on a normal Kubernetes cluster. It's painful, right? This gives you just one single template to just apply. Then the final bit. I had an AI application which was doing real-time translation between languages. So it takes an audio, converts it to text, changes the language, and then converts the text back to the target language. So try to demonstrate English to French. Unfortunately, I was not able to play the audio back, but then yeah, that's the entire flow. Then we try to scale it up. I had developed a script wherein I was sending continuous concurrent requests. And as soon as KServe saw there are so many requests coming its way, it spun up another pod because we had set the maximum scale to 2 for Whisperer and Workstraga. Whereas for LexiShift, the text-to-text conversion, it just stayed at 1 because it was still able to handle this load with just one pod. So this is the catalog I mentioned, catalog.cordent.io. As you can see, like we have a bunch of templates already provisioned here. Like if I just open kubectl, right? This is what you'd need to do. So you'd need to install the Helm chart, right? This would do two things. It would install a Helm chart and also your service template. So the kubectl Helm chart along with the kubectl service template is installed together. So with just this one command, you're good to go. And then in your cluster deployment, you mention it like this. And of course, values.yaml is configurable, right? So based on your requirement, you can modify this, right? So basically, this is what I want to show you that catalog.io, catalog.cordon.io is there. And this list is expandable. We are like constantly adding more and more charts here. And in case like you guys are interested in any other ones, like the car scheduler is something that I've heard multiple times, and that can just be added here as long as there's a help chart. And I'm sure like most of these projects have help charts already, right? And then there's the main website, docs.cordon.com, the documentation website, where we have a bunch of resources here in order for you guys to try out on different clouds. Admin guide, and yeah, I mean, you guys can explore this. I'll share these links post the session as well. So docs.cordon.io and catalog.cordon.io. All right, guys. Thank you so much for staying in and listening. I hope you enjoyed the session and took some value out of it. Let me know if you end up doing some other crazy things with AI. Just every day, there's just one new crazy thing. So, cheers. Thank you.